Welcome to this primer on graphs. In this lecture, we look at an application of the principle of double counting that we discussed the last time. And let us recall what is the principle of double counting. So it says that if we have a bipartite graph with, let's say, x and y serving as a bipartition of the vertex set, then counting the number of edges in the graph from the left side, from the point of view of capital X, is same as counting the total number of edges from the point of view of y. As simple as that. Okay, so now let's go to the application or illustration. So here is the problem. Fix a finite set X, and let's say we have subsets A1 up to AM of the set X. And here we are not demanding that these are pairwise distinct subsets or any such thing. There could be repetition here. They could all be the same for all we know. All right. Now, for any element little x of the set capital X, define this number f of x as the total number of indices I such that ai features x. So basically, we are counting the frequency of appearance of the element x in this list, which is why we have chosen the symbol f. And then this is what we want to show. With this definition in hand, we want to show that the sum of the cardinalities of all the possible intersections. So here note that AI intersection AI also appears because we are not saying that I less than j or any such thing. So sum of all the possible cardinalities of all the possible intersections is this number. And on the face of it, these two numbers, look quite different in nature, but this is true. So this may seem a little bit mysterious, but if you look at it right with the correct lens, the principle of double counting basically, then this would immediately fall out. And I encourage you to pause the video and set it up. I will show two proofs of it. One is using double counting. The other will use something else, which I find even more elegant. All right, so now let's look at the double counting proof. So we make a bipartite graph. We declare the set, so this set X was already given to us. So this is our set X. But what is Y? We define Y as all possible pairs of indices. So here there were m indices. We have just made pairs of those. So here I equals j is allowed, I greater than j, less than j, everything is allowed. So this is a set of size m square. All right, and now how is the graph defined? The vertex set of our graph is x union y. Let's not write that. What we will do is join x with I comma j in y if x belongs to ai intersection aj. Right, so this is when we will join an edge. Maybe it's good to make at least one edge. So maybe I'll make this. Oops, what is this? Yeah. So this edge will be joined, meaning drawn, if this happens. Otherwise, there will not be any edge between these two vertices. So some bunch of edges have been drawn. Now we will apply double counting. So what is the degree of x in this graph that we have developed? Okay, so how many indices I and j are there for which x lies in this guy? Those are precisely those indices I and j for which x lies in both ai and aj. Now there are fx many indices I for which x lies in ai and fx many indices j for which x lies in aj. And therefore, the degree of x in this graph is fx squared. So make sure you get this. And now what is the degree of this guy? So this is joined with a bunch of things, but which things? Those things which are elements of this intersection. So if we just find the degree, it is the total number of elements in this intersection. and hence degree of any I comma j, any point in the right side, is this. And now just apply the principle of double counting. You immediately will get this. All right, very nice. And you can experiment with this. Maybe you choose a specific finite set and specific subsets and just see that this indeed holds. That will be a good thing to do. Now let me show another solution. So alternate proof is this. We will look at characteristic functions. We discussed this in the primer on functions. So one just needs to observe that this function, which is a sum of bunch of indicator functions, is nothing but right? That's what this is, and this is just a nod to the following high school fact. What we are really doing is this, something that you must have definitely seen. This is all that we are really doing in the above thing, because what is the product of one AI with one AJ? That is this guy. So this is really what is going on in the above equation. But what is the above equation? The above equation, the right hand side is clearly the square of, let me change the indexing variable. It's the square of this thing, because this guy is same as that guy, right? This guy is same as that guy. So now we can just operate this on both sides. Now on the left side, we can interchange summations. Whoops, sorry about that. So what I wanted to say is, when we are operating, we are also evaluating the function at a point, otherwise it doesn't make any sense, right? So this is what we are doing. So this was a function with the domain the set x, and now it is consuming a point of x, so it becomes a number, and now we are just adding those numbers up, and similarly on this side. And now we can interchange summations, so it's good to skip a few steps and do it quickly. That's what we have. And the left side, so what is this? What is this guy? This is just the cardinality of the intersection of AI and AJ. So the left side is what we were looking for. But what is the right hand side? Just note that this is it's a small observation. This x can be kind of plugged inside. Just unravel the definition of everything, and you will see that this is the case. But what is this? What is this count? This is basically picking up, when does this become 1? It becomes 1 when x lies in AK, otherwise it becomes 0. So this is really the frequency of the appearance of x in any of the AIs, and hence this number is just fx. This number is fx, and that's it. That finishes the proof. So the proof is just this identity, right? So that's that. And one more comment. Here we could have taken 3 y's intersections rather than just 2 intersections. We could have taken 3 y's intersections, and here we would get a cube, and so on. So you can figure all of that out. And both these proofs will work for all of that. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.